So this lecture, this lecture is actually a part of many parts. I'm yet to identify how many parts of a series of lectures, because this Aqueous Solutions is actually has a very wide scope. It's one chapter in most chemistry textbooks, and thus the need for more than one videos for this in order to cover all of the topics involved. Now, for this video, I'll just be giving a short introduction to solutions, and also, since in this chapter we will be discussing solutions wherein water as a solvent. Thus, we need a deeper understanding on how water acts, as how water dissolves a wide range of solutes. What makes it earn the moniker universal solvent. Then after that, we will discuss types of aqueous solutions, or solutions wherein the water serves as a solvent or the dissoluting agent, and we'll also discuss some reactions that occur in aqueous solutions. There are actually three, where precipitation, neutralization, and redox or reduction oxidation reactions. However, I will not be including this in in this video. I will discuss redox reaction in a separate video because of the length of its scope. Okay, so let's start. Now, we know that solutions is an homogeneous mixture made up of two or more substances. However, the term solution is referred to usually homogeneous mixtures wherein the final phase, the phase of the mixture is a liquid. Okay. Now, solutions has two components: the solvent and the solute. Now, the solvent is the one that has the greatest quantity in the solution. While the solute, on the other hand, is the all other components whose quantity is lesser than that of the solute. So basically, the solvent dissolves the solute. Okay. Now that we've set the stage and house on the solutions, now we will discuss on why water is a popular solvent, or how did it earn its moniker, the universal solvent. Now, water is a universal solvent because it can dissolve a wide range of compounds, may it be ionic or molecular compounds. Now, because of this, water has become the mechanism on how the water dissolves substances has been extensively studied or scrutinized. Thus, there are many postulates observations that have been established on how water dissolves, and how water becomes a universal solvent. Now, one feature of water is that the electron density of water is not evenly distributed. Remember that your oxygen is more electronegative than hydrogen. Okay. Now, because of that feature, the oxygen has a greater propensity to pull electron density towards itself from the hydrogen atoms, thus making water molecule contain a partially negative end, which is on the oxygen atom, and the partially positive end, which is on each of the hydrogen atoms. Okay, so let me go back here. Now what? Sorry guys. Wait. So how does water dissolve, let's say, ionic solids, or rather ionic compounds? Let's take for example sodium chloride here that we see in this animation. If we water molecules, what happens that water molecules approach sodium chloride, and since opposite charges attract, the partially positive partially positive end of water is attracted to the anions, which is chloride in this case, and the partially negative end of water is attracted to the cation, which is sodium in this case. Now, now we can see here that water forms a cage around each of those ions, thus separating them from each other. Now, when it forms a cage, the partially positive end faces the cation, and the partially negative end faces the partially positive end faces the anion, while the partially negative end faces the cation. So now let us proceed on the types of aqueous solutions. Okay. So there are several types of aqueous solutions depending on the degree of the separation of the ions in the solution. So one is a strong electrolyte, or a strong electrolyte solution, wherein the ions are completely separated by water. So let's take for example, let's have our previous example, sodium chloride. Now sodium chloride, when they are in aqueous solutions, they dissociate into their respective ions completely. Can you see? Yeah, that's it. So they dissociate completely in aqueous in water. Oh, I should make my penmanship smaller. Sorry about that. So something like that. Okay. Now solutions. They are strong electrolyte solutions. They are very strong conductors of electricity, that as we will see later on. Okay. Another type of electrolyte solution is a weak electrolyte, or a weak electrolyte solution. Now weak electrolyte solution, on the other hand, dissociates also to its respective ions. However, they dissociate only to a certain degree. Unlike strong electrolytes that dissociate completely, weak electrolytes do not. So let's take for example acetic acid. Okay, note to self: make your penmanship smaller. Acetic acid, when dissolved in water, dissociate some of this molecules dissociate into acetate anion and H plus, or hydrogen cation. So it does not completely dissociate. This these two reversible half-added arrow here indicate that the separation of the ions of acetic acid in water is not complete. Okay. Next, we will go to the non-electrolytes, or non-electrolyte solution. Or rather, it's just written like this. So non-electrolyte solutions are, well, they just float there. They just float there. They do not dissociate or anything. they just exert electrostatic. Sorry, not electrostatic. They just exert intermolecular forces of attraction with water. So let's say, for example, most of your organic compounds that are soluble in water are non-electrolytes. Now, we will see here in our slide. Give me a minute. Okay. Right, that's it. Now, we will see there in our slide that that electrolyte solution conducts electricity. So, for example, we have a light bulb here that is connected to a power source, and the presence of the ions in the water will actually make a closed circuit, thus lighting the light bulb. A non-electrolyte solution, on the other hand, since it does not dissociate into charges, into charge atoms or cations, does not make it a good conductor of electricity, thus not making the bulb light here. Now, water inherently, in its purest form, does not conduct electricity at all. Since it does not have ions, well, technically, it does not have sufficient ions that can make it conduct electricity. We will see later on that water is not completely molecular in nature at all. We will see that in our other discussions. Okay. Now I will discuss the different some of the reactions that occur in aqueous solutions. Okay. There are three types of reaction that occur in aqueous solution or aqueous medium. So the first one that I will discuss will be a precipitation reaction. So precipitation reaction is, by its name, ions in aqueous solution react together to form an insoluble solid, which is what we call the precipitate. Okay, so let's take a reaction here. So lead nitrate or lead 2 nitrate will react. Okay, again, mark smaller penmanship, smaller handwriting. So we have lead nitrate here in aqueous solution. I hope you can see. That's it. Will react with, I'll move this one because this is quite lengthy. So will react with potassium iodide. I'll show you the balance equation na lang, to form the water insoluble lead iodide. Sorry. So this is solid, since it does not dissolve in water, and your potassium nitrate, which is aqueous. Oops. I'll move it here. Now, in this case, our precipitate here is the lead iodide. Since if you see it here, if you see it in our chemical equation, the lead iodide here is solid in form. That means it did not actually dissolve in water at all when it was formed. Okay? Now, because of that, since we're talking about ions, I will introduce to you another chemical equation, which is what we call the ionic equation. So, ionic equation, or rather, a complete ionic equation. A complete ionic equation is just a chemical equation. However, you break down all of the ionic compounds in water or in aqueous solution into its respective ions. Now, going back to our chemical equation here, to our molecular chemical equation here. This is aqueous Now, since the lead nitrate, the potassium iodide, and the potassium nitrate are all in aqueous solutions, that means they can be broken down into their respective ions. This one, we'll leave it as it is because it does not dissociate into ions in solution, because it does not dissolve in the solvent at all, which is water. So the ionic equation, therefore, will be Pb 2 plus for lead 2, which is aqueous. Then, since the subscript of nitrate here is 2, thus the coefficient of the nitrate ion will be 2. Plus, since the coefficient here of potassium is 2, so it will also be 2. Plus iodide, and will yield you into again, leave that be, and what do you call this? So since we have a complete ionic equation, we will introduce a new term, what we call the net ionic equation. Okay, I'll get another board. Don't go away. I'll be right back. So going back, I have introduced again another equation, which is what we call the net ionic equation. So net ionic equation is just it's just the what do you call this? It's just the the ionic equation without the non-participating ions. Now, the non-participating ions is what we call the spectator ions. Wait, I actually have a slide for that. I will just show it here. Okay. Wait. So yeah, so spectator ions is the one that does not participate. So the spectator ions is basically the one that remains ions or dissolved in solution on both the reactant and the product side of the equation. So going back to our equation here, which I will show. That's it. Now, going back to our complete ionic equation here, which among these remained ions in the solution? So obviously, nitrate, when it was in the reactant, before the reaction, it was still nitrate in aqueous solution, and after the reaction, I just forgot. I have a mistake in my net ionic equation. And after the reaction, it is still nitrate here. So your spectator ions will be nitrate. And your potassium, on the other hand, is the one and your potassium also rather remained ions in the solution. So it is aqueous, it is K plus in aqueous solution on the reactant side, and it's still K plus here on the product side. So therefore, listing down our spectator ions will be your K plus and your nitrate. Okay? Here. Now we go back to our presentation. So therefore, the complete ionic equation, which is I have indicated, which I have said earlier, is therefore in our example, which is I've not shown it here. Sorry. Our net ionic equation here, therefore, in the reaction that I have shown is this one. So since if you see lead here, lead 2 plus and iodide anion reacted together to form your lead iodide, which is the solid precipitate. So what does spectator ions do? So by its name, they just float there at the course of the reaction, and it does not. They do not actually participate in the reaction. So now, wait. Oops. So now we will proceed to neutralization or acid-base reactions. So neutralization reactions, or namely acid-base reactions, is by its name is a reaction between an acid and a base, and they will form salt and water. Okay. So let's have, for example, this classic acid-base reaction. So let's have this classic acid-base reaction. We need first to identify which is the acid and which is the base. So we have sodium hydroxide and hydrochloric acid. But well, obviously by its name, the acid is HCl, while the base will be your sodium hydroxide. Now for the sake of this discussion, although the definition of there are several definitions of acid, and it's quite complex, such that is reserved for a separate chapter in our Chem 115. Now, acid is the one that contains an H that dissociates into an H plus cation when dissolved in the solution, and the base is the one that produces an OH minus cation or anion or hydroxide anion when dissolved in solution. Therefore, the complete ionic equation for this one is Na plus aqueous plus your hydroxide anion, since this one will dissociate into sodium cation and hydroxide anion, plus H plus aqueous plus your chloride anion, which is a product of the dissociation of your hydrochloric acid, and they will react together to produce your sodium cation, since your sodium chloride is completely dissociates in the solution, as we have indicated in our previous example. And we have a product here which is water. Now, based on we have already know the definition of, we know what is a complete ionic equation and the net ionic equation, and what are spectator ions. We need to identify which of the following will be spectator ions here. Now, we have seen that sodium and chloride are still aqueous after the reaction. So this is our what do you call this? This is our spectator ion. So we will omit that in our net ionic equation. And since water is a liquid here, therefore water is a product of the combination between hydrogen cation and the hydroxide anion. Therefore, the net ionic equation will therefore be will therefore be H plus in aqueous solution plus OH minus in aqueous solution will react to form water. Okay, so this I will end our discussion for aqueous solutions for now. check out my latest check out my subsequent lectures for this chapter, for the whole topic aqueous solutions, and I'll also answer some problems. I don't know, maybe. And I don't have any closing remarks, so I believe this is the end of it for now. I'll see you guys in the next. I'm expecting, or I'm hoping, that you'll keep on subscribing to my YouTube channel and keep on viewing on this educational videos. Okay, see you